There we go. Okay. The next 4 or 5 chapters will involve the study of chemical reactions. There are 3 ways to study chemical reactions: chemical kinetics, chemical equilibrium, chemical thermodynamics. Chemical kinetics is primarily concerned with rates of reaction, speed of reaction. Chemical equilibrium is primarily concerned with the extent of reaction. We will explain when we get there. And thermodynamics is concerned about the feasibility of a reaction. That is, will it work or will it not work? Applying these can be individual to a given set of circumstances, or all 3 of them could be part of a research project that defines the nature and character of chemical reactions. We'll begin with the kinetics and develop it and go through equilibrium towards thermodynamics. Now, at present, I want to show the interaction of kinetics and equilibrium and how that collectively or together relates to chemical. Okay, you need a little XY, concentration against time. Simple. And generically, we'll take reactants going to products. So reactants are products P. At time equals 0, time equals 0. Am I listening? How much product do we have?
0.
0. There is none. 100% reactants. Now, as we go forward in a lot of the problems and concepts, I want you to think of this point as being like a horse race, and the horses are in the starting gate. They haven't been released from the gate yet. So the reactants are the horses before they react at some instantaneous 0 point. Now, allow the gates to open and the horses to run. What's the logical outcome in terms of concentration changes that the reactants and products are going to undergo? So this is logical. The reactants concentration is going to go down, the product concentration is going to go up. That's not a mystery. That's easy enough. So we see a trend that follows this for the reactants. They will start going down. But what happens is they begin to level off. They'll find a point out there somewhere to level off. At the same time, and this is a demo, the products, regardless of it, will follow the same issue, concept. Move this back a little bit. These are your products, and these are your reactants as a function of time. Now, looking at this graph, we divide it into 2 parts. At the point where the slope goes to 0, that is, you have a slope of 1 at the 0 point. Vertical is 1 is vertical slope. Horizontal is 0 slope. So we find that point in here, and we'll just assume this and here. That separates this into two distinctive parts. This portion from 0 to this point right here is called the kinetic region. And from that point beyond, out as far as the reaction will take itself, is the equilibrium region. Now, the significance of this kinetic region is you have no point in here where the slope is the same. Stays the same. It's constantly changing. So as we look at the slope at this point, it's a rather high positive slope. But as you move over to another point, the slope has decreased. Some people say the speed is decreasing. Actually, speed doesn't have really a signage. It's decreasing, but it's instantaneous because we look at speeds at individual points as you go along here. So all along this issue, slope is changing. That means speed is changing, it's decreasing. Same way here, it's negative slopes as you go through this, but until you reach the point right here where it transitions into 0 slope, no point at any point in time matches any other slope in that curve. This constitutes the essence of the kinetic region, or when you study a chemical reaction in terms of rates, you're studying them in terms of those changing slopes, how they change. Well, slope is a velocity terminology, a change in something over time. Speed is a change in something over time. So this rate is a change in something, which would be a change in concentration that we've spent so much time at the beginning of the semester studying as a function of changing time. And this concept right here defines what we call the rate laws. So kinetic region uses rate expression or this speed expression. Speed or velocity in chemistry is concentration over time. That's what it is. In mechanics and cars and is miles per hour or something else. But in chemistry is concentration changes. That's what we have to monitor as a function of time, right? I mean, how do you measure the miles per hour in a chemical reaction? You don't. Well, anyway, what this leads to in the kinetic region are rate laws. A rate law is a mathematical expression that defines the behavior rate of that reaction in terms of what we call rate factors. And I'll get to that when we start the specifics. So, for everything in here, when the data that you obtain has to do with concentrations and times, and then you take that ratio of concentration against time, come up with a rate, and then translate that into a rate law. And we'll show you what that means as we get into the topic and how to construct a rate law for a given reaction. At the point where the slope goes to 0, we transition out of the kinetic chapter and go into the equilibrium chapters. And actually, there are about 3 or 4 of them that deal with equilibrium concepts. But they are all based upon the fact that the concentration of products and reactants do not appear to change. This is called the law of mass action. When what happens here is what you're looking at is a case where the rate of reaction forward in a reaction, the reaction begins to reverse itself, so to speak, is equal to the rate of reaction in reverse. And again, as I was fixing to say, this is the law of mass action. If you can read that, law of mass action. And says that we have reached a condition whereby in this chemical reaction, the reactants are producing products at a rate equal to products producing reactants. Probably an example of that is you took a container of tap water on a hot day in a clear glass container, put a top on it where it couldn't evaporate away, and you come back after a few hours, the amount of water would appear to be the same. It may be hotter because of the sunshine, but just looking at the volume that you started with against the volume that just a couple hours, it's the same, because the rate of evaporation has reached a point where the rate of evaporation is equal to the rate of condensation. That is a law of mass balance. I mean, not mass balance, mass action, and defines equal rates of occurrence of something in a reaction. The law of mass action leads to a relationship which defines how far from the beginning of the curve here a reaction goes until it reaches this point where it transitions into the equilibrium region. And this space in here is called extent of reaction. What this, as some reactions, reaction number 1 goes to products, has a small extent of reaction. That means very low product concentration is produced. Whereas some reactions, say some other reaction goes to products, it produces a large, it takes a long time to get to that equilibrium point. Some of them instantaneously go into equilibrium. Some of them take forever to get to equilibrium. Large extent of reaction, and as a result, what this means is you have a very high product concentration produced. And these are defined by numbers, values, magnitude number. This is proportional to magnitude of number, some number. For a very low product yield, you'll have a small number attached to a given reaction. For other reactions that produce a lot of product, you'll have a large number, which says this is a large extent of reaction. goes a long way before it hits the equilibrium point. And these numbers are called equilibrium constants. And every reaction has its own personal equilibrium constant. Some are very, very small. Some are very, very large. But equilibrium constants are characteristics of a given type of reaction. Here is one on that relates to solubilities of salts and compounds, certain compounds, into how much will go into solution. How far will it go before it, how much will it deliver into solution? Going from solid into ions or something. I'll show you later, but anyway, let's take a look at some of the numbers here. These are your extent of reaction numbers. And they're called equilibrium constants. 4.6 times 10 to the minus 33. Itty bitty number. That means one molecule out of all the gazillions of molecules of aluminum hydroxide might go into solution. That's what it refers to. Barium chromate, 10 to the minus 10. None of these go into solution in great quantities. That's what it means. And so as we get into the equilibrium world, this is what will be your focal point right here. These kind of numbers. And what do you do with them? How do you use those numbers to understand the behavior of a reaction while it's in the equilibrium, wrong direction, sorry. While it's in the equilibrium region. So this is introduction. Says we're going to do certain mathematical evaluations in here that tell us about the speed and rate, behavior of a reaction in one context, but when we get over here, we're going to do something else that defines the nature and character of reaction in terms of this weird thing called an equilibrium constant. Bigger the number, the more product is generated. Smaller the number, the less. Well, that's just a generic outcome. Now, how do you use that to get some specifics about the nature of a reaction is what I'm trying to teach you and what my job is in teaching.